And let's see if this is going to give us the right answer, because, so we have n, and the number of 2 cycles, 1 2 cycles, and 2 1 cycles is going to be, well, we are looking at factorial 4 divided by 2 to the power 1 times 1 factorial, and then we have 1 to the power 2, and then 2 factorial, right? So here we see in the denominator we have 4, in the numerator we have 4 factorial, so the result is 6, which matches the calculation that we did before, right?
Sir, could you please explain the to the power ji part?
Yeah, so when we had all the pi's different, we had just factors of pi here, right? But if you have more than one pi, then there would be, say, ji factors of pi. So then it would be raised to that factor. But those are, they can be exchanged, so that's why we have to multiply in the denominator by ji factorial.
So if all the pi's are different, then all the ji's are 1. So that makes sense.
Yeah,
okay, got
exactly.
it.
Yeah. Okay, so this is kind of, not really essential, but I think it's since we're doing some permutation, it's good to have some permutation like calculation. So the number of, the number of, this, so the number of different sets, right? So that for a given n, the number of different, subsets, say P1, P1, J1, P2, J2, dot, dot, say P, R, JR, it's called the partition. Okay, it's called a partition of n, or the integer partition of n. And it, this number grows very rapidly with n. And let me just give you an example. So for example, if I take the number 1, it has only one partition, which is 1. The number 2 has one partition as well, 1 plus 1. Number 3 has several partitions, 1 plus 1 plus 1. It also has a partition 2 plus 1. The way we are counting it, 1 plus 2 is not a different partition, it's the same partition. And number 4 has 1 plus 1 plus 1 plus 1. Then I think 1 plus 1, sorry, we want to have the big numbers first. 2 plus 1 plus 1. Then 2 plus, say, 2 plus 2. And then we have 3 plus 1. And then we have...
I think that's all.
Would the entire thing be a partition?
Yeah, it's a trivial part. Yeah, exactly. So So this is actually the interesting thing is that there are no general formula for Pn, the number of partitions, right? Pn. Okay, so this is not known. What is known is that there exists a generating function. So there is some function, and that function has the form of n Pn x to the power n, and that you can calculate Pn sort of like brute force from that, and that was derived by Euler. And Ramanujan found some partial results for this, and there is a formula for an asymptotic result. So there's an asymptotic formula. There exists an asymptotic formula for Pn, known as Hardy-Ramanujan formula. But we are not going to discuss these things because it'll basically take us out of group theory into the realm of number theory, and it's not a number theory course. But I just wanted you to know that there is some interesting mathematics problem related to the partition, to these partitions of the symmetric groups. Okay. Okay. Are there any questions about this derivation?
Sir, will we have like 3 and 2 in the previous page?
3 and 2 would be 5, right?
No, like
no,
3
like,
and 2 in the entries for the partitions for 2 and 3.
Sorry?
I mean, for 2 and 3, we miss the entire subset as a set as a partition. So there's a 1 plus 1, but not 2.
Oh yeah, you're right. Yeah, sorry. Yeah. Yeah. So yeah, I'm not sure if this is, I think it is, yeah, it is like included in the partition, right? Is it? Yeah, I think so. Yeah. Yeah, it is also included. Yeah, thank you very much. Yeah, sorry for that. All right, so any other questions?
Does not taking anything include as a partition?
No. You basically, essentially, this is kind of, you see something called a partition function in physics a lot. They're kind of related to this. And what in physics, the way this thing emerges is that, suppose I give you some units of energy, say in quantum physics, especially some units of energy, right? And you are asked to, divide this up into different states. And basically, a lot of the partition functions, what they do is that they count how many ways you can divide it up into different states. Okay, so no, yeah, not having a partition, not like 0 is not a partition because all the stuff has to add up. I mean, think of how we derived it, right? We derived it as the number of elements in a subset with non overlapping cycles, right? So would there be anyone where there are no cycles?
Oh yeah, I see. I get it. Yeah.
Okay, let me see if there are any questions in the chat box. Nope. Okay. All right. So if there aren't any more questions, let me move on to the next topic, which is like talking about group homomorphism and setting the stage for the first isomorphism theorem. Okay.